No. Nope. Okay. Oh, really cool. Saw math in real life. So I am putting in a wood floor. We are. But this connects to math. So I'm putting a wood floor, and the fact is that my house does not sit flat. The floor, there's kind of it's lower on the edges, and in the middle, it's kind of raised up. But the fact is, when I lay down the wood floor, I lay down these like little 12-inch pieces, right? Okay, 18-inch pieces. And the fact is that they lay fine. Why? Because of linearization. Remember yesterday we talked about it in short spaces. Looks like it makes a line, even though it's a curve. Short spaces makes a line. I look at my four, I'm like, got derivatives all over the place, man. Yes, yes, Maya. Yes, that's how I think. Are you ready to judge me on that? Okay. Riker, do you have a problem with me? Do you like my example of linearization in real life? Oh my gosh. You think it's okay. Connor, like my example? Thanks, man. Air Nux. Boom. All right. So, linearization is one way to be able to approximate change in a closed period. So, for example, the function and the line are nearly identical within a small window. Okay, as you move further out, you can see that they start to separate, and they're not good approximations of each other at all. Well, linear approximation is one way to be able to approximate these values. The other one is to use what we call differentials. And we say that dy over dx equal to f prime of x. If I multiply both sides by dx, I get dy is equal to f prime of x dx. What that means is the change in y will be approximately the derivative times the change in x. Let me show you graphically what this means. And this is the most difficult part for people, is to understand what the graph means. Okay? We're going to talk about this. We're going to use delta y over delta x. Delta x is the change in x for the function. It is this amount, delta x. And then the change in the function for the y value is delta y. Is everybody okay? Y'all okay with that? We say that dy and dx refers to the derivative or the linearization. So this is going to be the same thing as dx. If I move over x, then dy is simply the change in the y value for the linearization. So delta x and dx are the same, but dy and delta y are not the same. Would you agree that dy and delta y, they're definitely not the same in this situation? But would you also agree that if I move closer to this red window there, if I move closer, would you agree that dy and delta y get a lot closer together? So why would the differential of a function be useful? Helps us approximate in small windows. Because some functions are really difficult to calculate. We gave the example yesterday, Isaac Newton trying to find the square root of 3.99. We gave a really good approximation of it. We're going to just do the basics right now. It says find the differential dy and evaluate dy for the given values of x and dx. So it says y is equal to 3x minus 1 over x for x equals 2 and dx is 0.5. No problem. All we say is that dy, the differential, is f prime of x dx. By the way, you get your notes for this test. Did I tell you that? So dy is, what is f prime of x? Anybody? 3? Very good. Riker's got 3 plus 1 over x squared because he said this is minus x to the negative 1. So he dropped the negative 1 in front and he reduced it by 1. Everybody good with that? I'm going to take that and multiply that by dx. That's the differential. We're going to use the differential to approximate a value, namely this value. Suppose we change a certain x amount, what would be approximately the change in the y? If I go over something, what would I go up? Well, we figure it out by using x and dx. So dy is 3 plus 1 over what? What is x? 2. So I got 1 over 4 times dx. dx is 0.5 or 1/2. So dy is, what's 3 plus a 4th? 13/4 times a half? 13/8. So that means if I go over 0.5, the function goes up approximately 13/8. Okay? If I go over 0.5, I go up approximately 13/8. Try next one. dy equals f prime of x dx. I have to find the derivative of 3 over x plus 1. How do you do that? Bleh. Quotient rule. Quotient rule works. There's an easier way to do it. 3 times x plus 1 raised to the negative 1. What rule do I use? Chain rule. 3u to the negative 1, x plus 1. What is the derivative of x plus 1? 1. What's the derivative of 3u to the negative 1? Negative 3 over u squared. So I get negative 3 over x plus 1 quantity squared dx. What do I plug in for x? 1. So dy is equal to negative 3 over 4 then, times dx is 1 over 100. I'm thinking negative 3 over 400. That means if x changes 100th, then y changes approximately negative 3 over 400. Again, it's not the exact amount of change. Just recall, again, the exact amount of change would be delta y. We're finding dy. That's the amount of change in the y. You're going to see the application in real life here coming up not too long. Let's just try let's try to actually draw the picture now. Compute delta y and dy for the given values. Sketch diagrams showing the line segments with lengths dx, dy, and delta y. I first start by drawing the function. What does it look like? Yep, shifted up 1. Everybody okay with that? So I'm going to go over 1 unit because it says x is 1. And that is the location at which I will draw my tangent line. The tangent line is an approximation for the function in a small window. What I would like to do is I would like to move over delta x. What is delta x? 0.2. So dx is delta x, which is 0.2. Okay. So I'm going to move over that amount, which would bring me to what x value? Yep, it would be at 1.2. Okay. One of these is delta y, one of them is dy. Do you know if the big one is delta y or the small one is delta y? Do you remember? The big one is delta y. That's the actual change in the function. Dy is this one. It's the change in the tangent line. It's an approximation. Okay. Could you draw those segments if you needed to on your own? Great. Let's compute dy. How do we compute dy? What's our formula? What is f prime of x? 3x squared. What is dx? Dx is 0.2. It's the same as delta x. Delta x and dx are the same. I have my differential. I can now plug in my values to approximate what dy is. Dy is, what do I plug in for x? 1. So 3 times 1 squared times 0.2, or 1/5. And I get 3/5. So that's saying if I move over 0.2, I move up approximately 0.6. Now, is 0.6 an underestimation or an overestimation for what I actually go up? It's an underestimation. Would you agree? Let's find how much we actually go up, okay? It's not that bad. What's the y value here? If I plug in 1, what do you get from the function? What do you get if you plug in 1? You get 2. Is everybody okay there? And then I'm going to find out this spot right here. What x value would I plug in to figure out that spot? 1.2, right? So let's plug in 1.2 to our calculator. Let's see what our actual value is. Not working. So I've got 1.2 raised to the third power, and then I'm adding 1 to that, and I get 2.728. We go back to our graph here. So this is 2.728. So if that's 2.728 and that's 2, what is the true value of delta y? Yep, 0.728. So 0.6 is an underestimation. We can see it's relatively close to 0.728. Flip it over. Time for you to try to set this one up on your own. Okay, let's take a look at our graph. Did everybody get the graph of the square root of x minus 2? Did you see we're at 6? Just to be clear, if you plug in 6, what is the y value at the spot then? It is 2. Very good. So then we're going to move over 0.1. I know that moving over 0.1 is really doesn't fit in with the scale of my graph, does it? But I want to be able to see it. So if I move over 0.1, this smaller one is actually delta y. This time the smaller one is delta y because it's the distance from here to your function. The distance to the tangent line is dy. So is dy an overestimate or an underestimate of delta y? It's an overestimate, okay? So we're going to compute these. We're going to start by computing dy. How do I compute dy? What do we do again? F prime of x. How do I find the derivative of root of x minus 2? Chain rule. U to the 1/2, x minus 2, derivative of x minus 2 is 1, derivative of u to the 1/2. 1/2 roots of u. So I've got 1/2 roots of x minus 1. Or x minus 2. Sorry. Times dx. All right, what do we put in for x? 6. So you got dy is equal to 1 over, if you plug in 6, what do you get in the denominator? You get 4, good. Times, what is dx? A 10th, so 1 over 10. So it looks like 1/40th is approximately dy. We know that delta y is going to be smaller than that, right? We know delta y is going to be smaller than that. Let's actually find delta y. In order to find delta y, we take this second y value and we subtract 2. How do I find that second y value? What do I plug in for x? 6.1, very good, because you moved over 0.1, so you're at 6.1. So I've got square root of 6.1 minus 2, so 4.1. And I get that, and I'm going to subtract 2 from it. So 2.0248 minus 2 is 0.0248. I wonder how close that is to 1 over 40. How good of an approximation is it? Pretty good. Yeah. Good? All right. Let's try some cool problems like we did yesterday. Okay, we got this and we'll be done. You want to approximate square root of 64.3. Square root of 64.3. Okay? All right? I'm going to make an x value, and I'm going to make a dx value, and then a given function as well. Can you tell me what is an x value close to 64.3 that you know the square root of? 64. So how far would I move over? 0.3. And what's the function that we're using? Anybody know the function that we're using? Square root of x. That's our function. So we have f of x is equal to the square root of x. Our x value is 64. Our dx is 0.3. Let's find the differential, okay? Because I know that the square root of 64 is 8. So the question is, if I go over 0.3, how much should I go up? So if we know the square root of 64 is 8, should I go up like 0.1? Should I go up 0.2? Like, what? How much do I go up, right? Let's figure that out. F of x equals square root of x. So therefore, dy, the derivative, what's the derivative? 1 over, or, yeah. What is the derivative of the square root of x? 1/2 roots of x. Like that. Dx. So dy is, what do we plug in for x? 64. So what do you get for that fraction? 1/16. What is dx? 3 over 10. So that means that the square root of 64.3 is approximately 3 over 160, right? Wrong. That's how much we go up. We go, so we know the square root of 64.3 is approximately what? It's close to 8, right? So from 8, you go up 3 and 100, or and 3 over 160. So 8 and 3 over 160. That's approximately the square root of 64.3. Let's see how close we are. 8 plus 3 divided by 160. I get that. If I take the square root of 64.3, What's your x value here? Not 4. 3. What's your dx? 0.01. What's your function? X to the 4th. So dy is 4x cubed dx. 3.01 to the 4th. Somebody estimate it. It's going to be close to what? Close to 81, right? Somebody ate a bowl of silly for lunch. So 3 to the 4th power is 81. So we know it's going to be close to 81, but how much do we move up from 81? And that's going to tell us it. dy is equal to, what do we plug in for x? 3. So 4 times 3 cubed times 1 over 100. What is 3 cubed? 27 times 4, 108 over 100. 108 over 100. Or 54 over 50. Or 27 over 25. Right? So it'd be 81 plus that, or 82 and 2 over 25. So that's our approximation. Let's see how close we are. 3.01 raised to the 4th power. I get 82.08. If I take 82 and add it to 2 divided by 25, I get, hey, pretty much spot on, huh? Cool. Very good. Okay, last example. Turn to your notes to the last problem. So, anything that has the shape of a circle, I use the example of a disk drive. Radius of the circle was measured and found to be 5.4 centimeters. So radius is 5.4. With possible error of at most 0.1. So that means the change within the radius is at most 0.1. So we're going to say that r prime, the change is at most 0.1. What is the maximum error in using the value of the radius to compute the area of a circle? What is the area of a circle? Pi r squared. Let us take the derivative. Derivative of a is a prime. What is the derivative of pi r squared? 2 pi r prime. So he's able to take the formula and say the change in the area, if we are off by 0.1 centimeters in our measurement, how will that affect the area? Well, it's 2 pi times, what's your current radius? Times 5.4 times, what is your, this would be your delta x. That would be your change. That's the language that they're using, times 0.1. I know it sounds nerdy, folks, but guess what? The people who are going to hire you someday, they want you to be super nerdy about what you're going into. They want you to love it. They don't want you to just like, oh, I want a good job and I want summers off. They want you to be geeky about it. They want the best. So use the lingo, use the language. The area is going to change by 3.39 centimeters squared. Now, I don't know if they're okay with that or not. But they're going to see that, and they're going to say, okay, 3.39, that's within our tolerance of what we can accept. Or they're going to say, forget it, we got to go back to the drawing board. I will miss you guys Thursday and Friday. Trust me, I'd much rather be here than in drunken Scottyland.